Okay, so we are in generalized linear models with examples in R, and we're in chapter 2, and we're on question 10 of chapter 2, so 2.10. So this is a three-parter, and so we'll look at each of these as we go along here. But for each of them, we are to assume that a quantitative response variable y and a covariate x are related by some smooth function f, such that mu equals f of x, where mu is the expected value of y. Okay, so hopefully that makes sense. So we have three parts here. And the first part is assuming that the necessary derivatives exist. I'll talk about what that means. Find the first order Taylor series expansion of f of x expanded about x bar, where x bar is the mean of x. Okay. So if you're not familiar with Taylor series, probably a lot of that is not going to make sense to you. I will kind of talk about Taylor series here, but I'm also going to refer you to some resources that will do a better job than I will. So what is a Taylor series? Okay, well, the place that I would refer you to is to go to Khan Academy, and I think this link takes you to a playlist on Khan Academy that talks about Taylor series and their cousin Maclaurin series. But generally, a Taylor series is a way of expressing any smooth continuous function with a polynomial series. Okay, so I'll give an example here in a second. But what's important here is that we have smooth continuous functions, okay, because only smooth continuous functions have derivatives, and the Taylor expansion is going to use derivatives, okay, and maybe you can see some of them in the notation down here. And so when the question says, assume that the necessary derivatives exist, part of that statement is saying, assume that the relationship between y and x is a smooth continuous function. Okay. So generically, a Taylor series looks like this. So say that I have any relationship between y and x, and it's a function of x, so f of x. And regardless of what this function is, I can exactly equal it. So regardless of what form this takes, I can find an alternative form that looks like this over here, and I'll break that down in a second, that exactly equals f of x, whatever f of x happens to be. Okay. So this is the generic form of the Taylor series polynomial. Okay, so it's a sum of these different terms here. Okay, and so I'll break some of these terms out here in a second. But roughly what we have is we have the nth derivative, so n goes from 0 to infinity, of the nth derivative of f of x taken at the value k divided by n factorial multiplied by x minus k to the nth power. Okay, so for example, when n equals 0, we have this term here, right? So we have the 0th derivative taken at k, where f of x, where x equals k, divided by 0 factorial, which is just 1, and then x minus k to the 0th power, which again is just 1, okay, plus the first derivative taken at k, divided by 1 factorial times x minus k to the first power, and so on and so forth. Okay, so we can further simplify this. So if we take this whole expression here, right, because x minus k to the 0th power is just 1, then we multiply this thing by 1, and so we can just ignore that, right? So you see that its simplified term here doesn't have the x minus k. Because 0 factorial is 1, we don't have to have f of x or f of k as a fraction, okay? And then the 0th derivative is no derivative at all. It's just f of k, right? F of x at x equals k, okay? So that's the first term. Now if I go to the second term, now I have the first derivative of f at k divided by 1 factorial, okay? If I divide anything, so 1 factorial is just 1, so once again I don't need this to be in the form of a fraction. And now I have x minus k to the first power, which equals x minus k. So I can write that term like this. Okay? And again, for the second and third terms, right, you can just kind of go along and convince yourself that that pattern persists. Okay. Okay, so now in practice, we obviously can't and won't calculate infinite terms. We're going to calculate a few terms, and then everything else we're just going to ignore, which is okay because, well, in certain contexts it's okay. But that's what we're going to do. All right. So in our context, and this is what the question asks us to do, or this first part of the question, is to find a first-order Taylor series expansion of f of x expanded about x bar, where x bar is the mean of x. Okay, so we have that mu equals f of x. Okay, and so now the x bar is our k, and so I can just basically substitute x bar for k and just kind of plug everything in, and so this would be our Taylor expansion. Okay. All right. So now we want to rearrange our Taylor expansion in the form of a multiple regression model. Okay, so now my first inclination in doing this is different than what the book suggests that we do, and I think that what the book is suggesting is important for what comes in part 3 of this question. So first I'm going to present how I initially would be inclined to answer this, and then how the book wants to answer this. And I think that they're probably both valid. So anyway, the first thing to notice, talking about how I want to approach this, the first thing to notice is that our expression here, okay, reproduced here, is linear. It is a linear function in x minus x bar, right? So if I were to look at this, and everywhere where I have my f to some derivative, whether it's the 0th or the first or the second derivative of x bar, if I were to say that those were like the beta coefficients, and x minus x bar was the data thing, was the data element, and so I'm going to call that z instead of x minus x bar, well then this equation, if I just substitute that notation, looks like this, and that is, right, and so this is a multiple regression model. That's what it is. Okay. But the book doesn't want us doesn't want this expression in terms of being linear, or doesn't want an expression that is linear in terms of x minus x bar. It doesn't specify this in the question, but in the answer in the back of the book, it alludes to this. It wants linear in x, okay, not x minus x bar. Okay. So now the answer in the back of the book is not very informative, unfortunately, but it's f of x is linear if x minus x bar is small. It should be f of x is linear in x if x minus x bar is small. I'm going to change that. Okay, so this is a true statement, but why is it true, or how can we see that it's true? Okay, so if I go back up here, so imagine very small values of x minus x bar. Say that x minus x bar is 1 or less, or the absolute value is 1 or less. Okay. Well, then all that we're doing is we're saying that mu is equal to just fractions, where each fraction is less than 1, of each of these. I'll call them derivative terms, but of course some of the derivatives are fractions where they're being divided by n factorial or whatever. But anyway, but then we're just basically adding, right? We're just adding approximately these derivative terms, okay? Because these values right here, they, at most they approximate 1 or -1, in which case we're just adding this, or they're approaching 0, in which case that whole term just drops out. Okay. Now, but imagine what happens when we're far away from x bar. In other words, x minus x bar is large, and for this we'll just say that x is greater than 1. Well, then all of a sudden, some of these terms, especially as we start to have exponents in the x minus x bar, like x minus x bar squared or cubed or whatever, those become very large numbers very, very quickly. And so now all of a sudden the relationship between x and mu is not linear at all. It becomes super linear, or I'm not sure what the right term is, but you can see that as that happens, as this value gets, exceeds 1, then all of the corresponding terms become really, really big in a nonlinear fashion. Okay. So the reason that I think that the book wants to frame this question in the way that it does is because of part 3. So in part 3, we want to explain what this implies, or explain how this implies that regression models are locally linear. So just to expand that question a little bit, explain how this approximately linear behavior when x minus x bar is small, how that implies that models are locally linear. Okay, so what do we mean by locally linear? Well, it means that when we're somewhere around x bar, right, when we're just a small distance away from x bar, that our Taylor series approximation is linear in the way that I've just described, right? That the changes in f and x, or f of x, are changing linearly, not superlinearly, with changes in x. The reason that it's local, of course, is that as we get far away from x bar, in other words, as x minus x bar becomes large, we're not, there's a good chance that we're no longer linear, okay? And so this type of, regression presented like this, or I shouldn't say regression presented like this, but this presented as a regression then is linear in the local region around x bar, okay? So now I think that the reason that this is important is because we will often encounter situations where we presume or have strong reason to believe that the relationship between y and x across the entire domain of x is not linear, right? However, because of this, I guess we'll call it a finding of local linearity, we can have some confidence for the relationship, the inferences of our model that are making inferences about the relationship between y and x, we can have some confidence in them even in a non-linear context when we are not that far away from some focal point like x bar. Okay, I think that theme will probably pop up a few more times as we scroll through the book, but it's just maybe something to keep in the back of your mind right now. Okay, that's it for this.